So the next 1 hour or so, we are going to spend on looking at the calculation of the other risk index. We have been talking about the loss of load expectation all morning. Now we are going to shift our emphasis on the loss of energy expectation, yeah? Because we know that many systems are energy limited, especially with the advent of all these renewables, solar, solar, wind, geothermal, and all those. So they all have energy limitations. They don't have capacity limitations. So far we have been looking at capacity limitations more. In the future, we expect that there will be more focus on the loss of energy method rather than the loss of load method because of that. Okay. So calculations, we need to look at the load duration curve. Why? I mentioned earlier that the load duration curve is an hourly curve. Therefore, the area under that curve is actually the energy demand of the system. So that's what we need, right? If we know how much energy is required in the system, our objective now is to find out how much energy we are not able to supply due to those situations when there is loss of load, okay? So it's just an extension of the loss of load expectation method to calculate the energy not supplied. We can also calculate some of the other indices that I mentioned perhaps yesterday or the day before, the energy index of unreliability as well as the energy index of reliability. Now the reason why we calculate these indices is that we want to compare two totally different systems on the same pedestal. That means they may have similar peak loads, they may have similar generation composition, but once you want to compare different configurations for the future, it is always better to compare them on a per unit basis. So that's the reason for the EIU and EIR, energy index of unreliability and reliability, to be used sometimes. I also mentioned another index again yesterday, if I'm not wrong, system minutes, SM. You remember SM? And the often quoted number is 25 system minutes, which actually means that for 25 minutes, the energy will be lost at the time when there is peak load. That's the actual meaning, yeah? But usually that number is much higher. You saw one example today in the morning, and again we'll see an example. We'll see system minutes is much higher than 25. So we go back to the curves that we saw in the morning. Remember the O subscript K? Yeah, we are going to use the same notation. What is O outage? Outage, O1, O2, O3, and then small p, P1, P2, P3. And now we are adding another index, another number. It is called E subscript K. So E is the energy curtailed by a capacity outage, OK. Energy curtailed, not energy supplied. Energy curtailed, not supplied, okay? So that's what we will see when we look at the graph. And how we'll calculate the LOEE is very similar to how we calculated the loss of load expectation. Instead of PKTK, we've got PKEK, right? Because this one deals with energy curtailed. That one dealt with the load curtailed, right? So that's why now we have energy in the equation. So again, just to understand the concept, this is our installed capacity. This is the time, the load duration curve over 0 to 100% of the time, which could be a daily, which could be monthly, which could be annual, doesn't matter. And if there is a capacity on outage OK, which may be O1, O2, O3, then you can see that we are not able to supply this much of energy after that capacity outage takes place. So our objective will be to find this E subscript K, and we already know the probability of that happening because we know the probability of this capacity outage, right? So therefore our calculations will become quite simple. If we normalize it by the energy demand, the total energy under the load duration curve, we can find the total energy under this curve. If we normalize it, we will get the energy index of unreliability. Usually the EIU is a very small number, 0.00000016. It has a string of zeros. whereas its complement, called the energy index of reliability, is actually a string of nines, 0.99999 something. And then the system minutes can also be calculated. It is the energy unsupplied over the peak load. That's the definition, right, of system minutes, which I just now repeated as well. And I'm multiplying it by 60. Why? Because the energy, loss of energy is in megawatt hours, right? So I need to convert it into megawatt minutes. So that's why we get the system minutes by multiplying by 60. So peak load, and this is the risk index in megawatt hours. So although the loss of energy approach has perhaps more physical significance than the loss of load approach, which we saw earlier today, but it has limited applications. We haven't been using it as much. The most popular index, as you have heard me say, is still the LOLE, not the LOEE, yeah? As it happens, because maybe it's simpler to calculate, maybe from a customer perspective, hours per year, days per year is enough, yeah, rather than energy. Not many people understand energy, yeah, but hours per year is easier to interpret, so maybe that's one of the reasons, okay? So we go to our example, yeah, the famous way of learning, and we go back to our same system, 425 megawatt, 1% unavailability generating units with an annual load duration curve between the 100% and the 40% points. So the load, maximum load, system peak load is assumed to be 80. So 80 represents the 100% point, and 80 times 0.4, 32 megawatt will be the lowest load point. And it is a straight line, so that makes our calculations easier. The objective is to determine the EE, energy supplied by each generator, and the risk, loss of energy expectation. So the good thing about this method is that you not only calculate the risk, you also calculate how much energy each generator is supplying. That is a byproduct of the method. So in a way, you are getting more information as opposed to the loss of load expectation method. So let's look at this system data, 25 megawatt, 1% FOR. You know how to calculate the COPT, correct? Now, this information here is not needed for our calculations for now, but I just want to explain a little bit on this. What are the operating costs in any system? Anyone? What are the operating costs? What do they depend upon mainly? Fuel, correct. Operating costs come on fuel. That's why they are variable. You can also call them variable costs. What about the fixed cost? Installation. You pay interest, yeah, or rent, yeah, insurance, and all those things. So they are fixed. They do not depend upon, the one generator being out of service or not producing its full capacity. Nothing. It's constant. Every year you pay the premium, insurance and rental and whatever else. So that's why it's called fixed cost. So if I have these two data, I can actually calculate the total cost of generating that much of energy using the operating cost as well as the fixed cost. And that's very, very useful to the system planner when you can calculate the total cost of production of a certain amount of energy. So we'll not use this for now, but I just wanted to tell you where these numbers are coming from and how we can use them, okay? So in our case, we have a straight line from the 100% to the 40% points, and the peak load is 80. So you can find the equation of the straight line, y is equal to mx plus c, and this is how it turns out to be. Now what is the area under the load duration curve? So if you look at this graph here, yeah, this is the time 0 to 8760. This is the load in megawatt. So the peak load is 80, the lowest load is 32, right? 40%, correct? The load varies from 100% to the 40% points as a straight line, and the peak load is 80 megawatt. So it varies from 80 to 32, correct? So the equation of the straight line, y is equal to minus 0.6x plus 100. We just saw that. So initially, when no generator is loaded in the system, what is the energy curtailed? If no generator is loaded in the system, I'm not supplying any energy, correct? I'm not supplying any energy. That means the total area under this is the energy not supplied. energy curtailed. You can find that. You can find the area under this triangle. You know how to find that. Half of base times the height. And you can find the area under this curve. That's 32 times 8760. And then you can add them up. So you know the total energy required by the load, correct? So the total energy required by the load turns out to be 490560 megawatt hours. So this is our expected energy not supplied before any generator is loaded. So I call it EENS 0, before any generator is loaded. Clear? Now we start to load generators in a priority loading order, economic loading order. Why do we do that? So this goes back to the operating cost. If the fuel for generator A is costing me less, I'm going to load it first. Yeah. If the generator 1 is costing me more, I'm not going to load it first. So that's the reason why I've just shown this data and why I'm loading those generators as A first, followed by B, then C, and then D, because operating D is more expensive and I wouldn't want to, make the costs go higher. So we load the first unit in a loading priority order 1, and once the unit is added, then I have two states. The generator is either out or it's in, correct? So capacity in is 25 or 0. Capacity out is 0 or 25. And we know the probabilities because we know that the forced outage rate of the generators is 1%. So we know the availability is 0.99 and the unavailability is 0.01, correct? So those are the two probabilities. Now energy curtailed, when the generator is out, I'm not supplying any energy, correct? I'm not supplying any energy. So therefore this is the amount of energy curtailed, which is the area under the load curve, correct? But when it is supplying 25 megawatt with a probability of 0.99, how much energy is curtailed? Let's take a look. If it is supplying 25 megawatt, that means I'm supplying this much energy, right? So how much is not supplied? That is this triangle plus this rectangle. You can easily find that area, and that's the number that you see in this particular table. So EK, PK or EI, PI, call it what you will, and then you do that weightage. It's an expectation. We have been dealing with expectations, right? Yeah. So we do that expectation and we sum them up, and this is the energy that is still not supplied after the first generator has been added, correct? So what does it mean? If this was the energy not supplied before the generator was added, and this is the energy not supplied after the generator has been added, so where is the difference coming from? From this generator. So that is why we can calculate the energy supplied by generator A as the difference of those two. So this generator is supplying this much energy. That's an added advantage of this particular technique. We also calculate in the process the energy supplied by each of the generating units. So now we load unit B. We load unit B, we calculate the new probability table, capacity outage probability table. You all know how to do that. We know the probabilities from the capacity outage probability table. We know the capacities CI, we know PI, we only need to know EI, yeah? So we already know for this state, when all the generators are out, when both the generators are out, we already know that we are not supplying any energy, isn't it? That means that we go back to this number, isn't it? And when 25 megawatt is out, we know how much energy is not supplied, is 271560. So you will find that many of the values are coming from that table. So only one new value you need to calculate. What is that value? Capacity out is 0, capacity in is 50. So let's look at that here. Capacity in is 50. So I'm here, right? I'm here on the load duration curve. So how much energy I'm not able to supply? It is this one, right? I can calculate that very easily using that triangle, and how much energy is supplied, obviously the remaining part. So I can put that number in, energy curtailed is this much. EI, PI, EI, PI, and then I add them up, I get this number. So what does this number represent? This is the energy not supplied after the second generator has been added. So the difference between this one and this one will give me the energy supplied by generator B, correct? So that's what I will get. The energy supplied by generator B is the difference between the two values. Okay. Now I add generator 3, yeah, unit number C. We call them A, B, C, D. So we add C. So we have one more capacity in the table. Of course, the probabilities will change according to the capacity outage probability table. And I already know these three values, remember? Those three values are from the previous table. You already know that. Now you need just one additional value. So capacity available is 75. So where are we now? We are here. Capacity available is 75. So we are not able to supply only this little energy here, correct? Which we can calculate as well. So that turns out to be this little value 2281. Again, you do EIPI, and you get this quantity. So after the generator C has been loaded, the energy not supplied is 4,709. And we can calculate the energy supplied by generator C. This quantity minus this quantity will give us the energy supplied by generator C. That's what it is here. Finally, you add the last generator, and this is your new capacity table, and you need one more value. But do you? What is that one more value? 100 megawatt is in, 0 megawatt is out. Yeah. So if you look at that, you are not curtailing any load, right? You are not curtailing any load because your installed capacity is 100 and the peak load is only 80. So therefore, there is no energy curtailed due to that. So it's 0. Yeah. 0. So this is also 0. You can add up the rest and you get this amount. So this is the risk in the system. I have now loaded all the generators in a priority loading order, and I find that the risk in the system is 137.89. Please note that if you do not load the generators in this order, you load them in any other order, the risk will be the same. The risk cannot change. So what will change? The operating costs will change. Fixed costs also no change. The operating costs will change. Therefore, the total cost of producing or generating energy will change. So that's the only other factor, but the risk is known. Once you know the generators, once you know their capacities, their availabilities, the risk is a given. The risk is fixed, okay? So 137 megawatt hours per year, you are not able to supply in this system. Another example, we have a load curve now where there is one straight line and there is another straight line. The peak load is 75 and the lowest load is 30 megawatt, and this is given over 100 hours. Duration can be anything. It can be a day, a month, a week, yeah. And 100 hours is very odd, right? It's not even a week, yeah. 4 days plus, okay. Doesn't matter, as long as you have the necessary data, you can do all the calculations. So consider this load duration curve for a period of 100 hours, the generating unit data given in the table. Assume that the economic loading order of the units is 1, 2, 3. So this is the generation data. We have the first generator which exists in 3 states. So it's a D-rated state unit which we just studied this morning. Yeah, the first thing from yesterday, right? We already know how to calculate the capacity outage probability table for a multi-state generator. Generator 2, the usual 2-state unit. Generator 3, the usual 2-state unit. So the total installed capacity is 25 plus 30 plus 20, yeah, 75, correct? No, 75 is the load. The total installed capacity is total installed capacity is 25 plus 15, 40. So this one is 40 plus 30 plus 20, 90. Yeah. Okay. So the total energy required by the curve, you can calculate, go back to this curve, you can calculate the total energy, right? This triangle plus this rectangle plus this triangle plus this big rectangle. You can calculate the total energy. Quite straightforward. That's why I'm using simple examples where you can verify all the numbers. So that energy turns out to be 4575 megawatt hours. Yeah? When no generator is loaded, the total energy not supplied is 4575. So when you add the first generator, it has got 3 states. It's not a 2-state generator, right? That's what we saw, 3 states. So if it is operating at 25 megawatt, the probability is 0.65. If it is operating at a derated state, its probability is 0.3. And if everything is out, the probability is 0.05. Okay? So we'll have 3 states in the calculations. When it is completely out, then this is the energy not supplied. When it is supplying only 15 megawatt, then the energy curtailed is 3075. So we are, I'm not sure if I've shown it in the curve, but you can calculate. When we have only 15 megawatt, we are here, right? So we are not able to supply the rest of the energy, right? Just like in the previous example. So similarly, you can calculate the energy supplied by generator 1 once you calculate this EKPK or EIPI after generator 1 has been loaded. And then you can continue the process, generators 1 and 2 loaded, yeah, and finally with the 3 generators loaded. You find that it is quite a long table because one of the generators is a 3-state unit. That's why it turns out to be quite a long table. So capacity in 75 all the way up to 0, and EI for 75 is 0 because it is just meeting the load demand, yeah. And then all the other cases there is some energy that is not supplied, and the energy not supplied at the end is only 64 megawatt hours for those 100-hour load duration curve. Okay. So this is the summary of the unit energy generated. First generator is generating 2000 megawatt hours, second generator is generating similar amount, third generator is generating only 337 megawatt hours. And the total risk in the system is 64.1 megawatt hours per period. Okay. 2 examples to illustrate to you how we calculate the risk and how we calculate the energy supplied by each generator. Okay. So the expected energy not supplied index 64.08. If you divide it by the energy required, total energy required, which is 4575, we saw that earlier, right? The total energy required is this one, 4575. So if you divide it by that, you will get the energy index of unreliability. And of course, its complement is the energy index of reliability. And then system minutes, you can calculate, you find 51.2. So more than 25, but this is also a very small system, so we can't draw any conclusions from that. For large systems, it will be much larger actually. 51 is still quite reasonable. But the often quoted figure in the literature is 25 system minutes for the system to be very reliable or highly reliable. Okay? So the determination of the expected unit energy outputs is a relatively simple matter in a system without energy limitations. But if the system is energy limited, then you have to consider that in your calculations. And the approach can also consider any number of units, derated capacity levels. We already saw that. One of the generators had derated capacity. And we can also include load forecast uncertainty, just like we did before the break. We did that for LOLE, but no reason why we can't do it for LOEE. It's the same. You have to do the calculations 7 times instead of 1 time. Okay? So the basic requirement is the ability to develop a sequential capacity outage table for the system generating capacity. Every time you add a generator, you have to develop the table. You add one more generator, you have to develop the table again, right? So obviously, if you write a software code for it, it's much easier. Hand calculations will make you repeat the calculations many times over. We can easily do a test for hand calculations, but doing a test on the computer is always harder, right? Yeah. So that's why I think these simple calculations are good. So another exercise for you, 3 non-identical 30 megawatt, 5% forced outage rate generating units and 150 megawatt, 6% forced outage rate unit constitute the installed capacity of a generating system. So it's 3 times 30, 90 plus 50, 140 megawatt. The load duration curve is represented by a straight line between the 100 and 80% over the 100-day period with a peak load of 120. Installed capacity is 140, the peak load is 120. Determine the system risk. Okay, similar to the 2 examples that we have seen just now. I'm sure you can do it, so there is an answer as well. Not sure if you can do it this afternoon because you have some demonstration of software, but hopefully you'll make time later on to check it out. Now there is another exercise here which is actually a very good question from my perspective, because it says a generating system contains 120 megawatt capacity in 6 20 megawatt units which are connected through step-up station transformers. So I think, as they say, a picture is worth 1,000 words. So this picture tells you what it is happening. There are 6 generators. They are all connected through step-up transformers to this generating bus, and then the load is assumed to be connected here. Okay, so that's what the scenario is, which I have described here. The generators have failure rate of 3 failures per year and 97 repairs per year, whereas the transformers have failure rate of 0.1 failures per year and a repair rate of 19.9 repairs per year. Notice the difference between the repair rates of the generators and transformers. You should be convinced, especially those working in the industry, that transformer needs much longer to repair, right? So the repair rate cannot be very high. You can't repair 500 times a transformer in a year. It takes much longer, sometimes weeks, to repair a transformer. Okay? So this is a very practical question. For an annual forecast peak load of 95 megawatt, calculate the risk LOLE, given that the annual daily peak load variation curve is a straight line from 100 to 70%. Calculate the energy index, unreliability, EENS, given that the load duration curve varies from 100% to 50%, and the answers are here. So how will you attack this question? How will you deal with this question? I haven't given you any example like this. This is different from the 2 examples. Anyone? Fantastic. These two are in series. We have already done series systems, series parallel, parallel series, mixed parallel, all kinds of combinations. So it's a piece of cake. You know, for 2 series systems, lambda is lambda A plus lambda B. Yeah. Similarly, you can find the mu or the R. So that's how you need to deal with this. And since all the 6 are identical, after you do that, you can use the binomial. Yeah. So therefore, it becomes quite straightforward. Obviously quite long, because I'm asking you to do 2 calculations using 2 different curves, not using the same curve. So it's double the work in a way. But that's what we do as students in order to learn more and more. Okay. So in conclusion, today mostly what we have dealt with, partially yesterday, but mostly today through chapters 7 and 8. We have shown the application of basic probability concepts to generating capacity reliability. We have shown 2 basic indices, the risk indices of loss of load expectation and loss of energy expectation, which is also called as expected energy not supplied or expected unserved energy. You can call it anything. The general notation you should know. This is the energy I'm not able to supply. Very simple. Whereas the loss of load expectation is, this is the number of hours per year that my load is not supplied, right? Or days per year that I'm not able to supply the load. So that's a fundamental difference between the 2. The LOLE technique is still the most widely used probabilistic technique because of its simplicity, perhaps, because there is a reference there, 0.1 days per year. This index has received some criticism because I must have mentioned when I introduced these indices that if the LOLP or LOLE is 1 day per year, for example, You don't know whether you are losing 100 megawatt or 1000 megawatt or 1 megawatt. It does not tell you the severity of the load loss. It only tells you that in the long run, the expected value will be X days per year or X hours per year. Okay, so may or may not have meaning to you. We need to understand that quite clearly. It is, however, possible to produce many additional indices. While we have focused on only 2 indices, LOLE and LOEE, no reason why you can't look at other indices. If you are interested in expected capacity shortage, you can define that as your risk, yeah, and therefore use the capacity outage probability table and calculate the risk of capacity shortfall. Or you can use this expected number of days when specified shortages occur as your risk index. So there are many risk indices you can create for your own system, but the probabilistic way of dealing with them will be the same, just the 2 indices that we have seen. The calculations will be very similar. Expectation, remember, expectation, EI, PI, or PI, PK, TK, or EK, PK, right? Depending upon whether you want energy or you want probability, or if you have capacity, then it could be CI, PI, right? So things like that. It is mainly a question of deciding what indices you want and then proceeding to calculate them. Remember always that the derived values are expected values, long run average values. You don't get to know their probability distribution. That's the disadvantage of the analytical technique. If you really want to know how they are described in terms of a probability distribution, you should go to Monte Carlo simulation. There is no other choice, if that is what is of interest to you. But when we do long-term planning, average value is good enough, right? We don't need to know how the index is described, whether exponential or Gaussian or whatever. The indices should also not be considered as absolute measures of capacity adequacy. So when we find the loss of load expectation, loss of energy expectation, we should realize that they are not 100% expressing the reliability or unreliability of the system, because we have made so many assumptions, correct? You must always not lose track of the assumptions. So they do not describe the frequency and duration. They only tell you days per year or megawatt hours per year. They're not telling you how many times in a year you will have outage, and every time there is an outage, how long will that outage last? Those are the frequency and duration indices. So we are not including those. We are not including operating considerations such as spinning reserve, yeah, dynamic and transient disturbances. I again refer you to the definition of reliability. It has 2 components, adequacy and security. We are dealing with only adequacy here, right? Not security. So therefore, the reliability indices that we are calculating here are not 100% representative of the entire system. They are only representing the static capacity evaluation, not the spinning reserve, not the dynamic nature of the system, not the security aspect. Indices such as LOLE and LOEE are simply indications of static capacity adequacy, which is what I just said, which respond to the basic elements affecting the performance of the system. You can include maintenance, you can include load forecast uncertainty, and still the calculated index will not be 100% representative. So you still need to go back and consider all this if you want it to be holistic, okay? However, when we do long-term planning, including maintenance and load forecast uncertainty, actually makes the index a little bit more realistic, yeah? And we can see the variation of the index. We can vary the parameters. We can do sensitivity studies and try to understand where we want to be in the future, how much we want to invest in the future. So there are advantages of what we have learned, but you must remember that we are still not including everything under the operation of the power system for the calculation of these indices. So this still does not make the index an absolute measure. It's a measure of the performance of the generating system, not the absolute measure, okay? As long as we are aware of that, then I think we are okay. Then we don't need to worry about it. So that concludes this particular chapter. We are slightly ahead of time.